Hello, everyone, and welcome. Today, I am presenting a class in industrial industry talk on the parametric modeling and automating the placement of universal TBM ring. I am Atul Tegar. I am working as a BIM specialist in COVI. About me, yes, I am a BIM specialist. I mostly works in the tunnel and other infrastructure projects. I have done my master's as a Master of Technology in Civil Engineering with a specialization in building structures. I, I'm having an experience of more than 11 years in the field of AEC industry. Most of the part of the experience as a structural engineer at construction site. And later on, I have more than 5 years of experience as a BIM specialist. I'm also Autodesk AutoCAD Civil 3D 2015 certified professional. That means that I work mostly on Civil 3D. I choose Civil 3D as my main tool to start any infrastructure project. I'm also contributing to the Civil Connection package that is for Dynamo for Revit, which is used for getting information or getting data from Civil 3D to the Revit. Being a BIM specialist in COBE, I'm mostly responsible for the digital development, parametric and computational design, and also for design automation. And also, I'm also assisting in Revit project setup, modeling guidelines, and also providing BIM trainings. Okay, in this class, let's discuss about the class. In this class, the learning objective of this class is first and is parametric modeling of the universal ring, how we are modeling the parametric modeling of these universal rings, how we are placing these universal ring along an alignment by following certain criteria. And we are exploring civil connection package, that is one of the package for in Dynamo that is used to connect Civil 3D and Revit. And then the last, we are just see how can we create a Python script in Dynamo to automate few things. Introduction. Yes, think deeper. Because when just nowadays in the modern society, when increasing the demand of new infrastructure, it is also posing a significant challenge in the infrastructure in cities across the globe. While much of the development is over the ground, as you can see, it's a roads, bridges, and many features are being driven underground. Tunnel is one of them. About COVI, COVI is providing solution for different services. Like we are providing services in architecture, buildings, in industry and energy, infrastructure, water environment, project management, and also for the BIM services. Here are the few iconic projects which COVI had did over the past few years. You can see we have some tunnels, London Area, United Kingdom, Oslo, airport expansion. We worked on the airport also, and many big infrastructure projects we had did. About the COVI tunnels. COVI tunnels are the world leading, especially in tunnels and underground infrastructure. We work almost in every types of tunnels. We also like working as an operation and maintenance of the tunnels. We also looking after risk management analysis. We're also doing MEP and service life design. COVI tunnel is having more than 450 skilled employees, which making it is one of the largest tunnel groups. COVI tunnel is working on different types of tunnel market segments. For example, metro, roads and rails, utilities, cavernization, immersed tunnels, hydropower, ground engineering, MEP, concrete technology, etc. About the TBM tunnel. Okay, so TBM tunnel are made up of some prefabricated concrete segment, which forms a ring in repeated series. And these particular rings are laid in succession, like one ring to another ring, and they are interconnected with each other by using of those mechanical connectors and following the course of the alignment. And the taper also in that each ring is having taper, like first the starting phase and end phase is tapered. Like for example, like if we have a curve along the alignment, so it means that the ring is tapered, like ring is having the less width along the curvature, and on the outer side it's having the more length. About the TBM tunnel, there are some parameters when we start to design the TBM tunnel. We need internal diameter. What is the diameter? Diameter can be fixed by the services, what is the use of that tunnel, and then we have to decide the thickness, what the thickness, that is purely based on the structure. We have different types of segmental ring system. It's parallel rings, ring and left rings, universal rings. In this class, we are mostly focusing about the universal ring. And we also have a different types of ring configuration. For example, in one ring, it can be having 4 plus 5 plus 1 or 4 plus 2. It means like 5 normal segments and 1 key segment. Another one is 4 plus 2 means a 4 normal segment and 2 segments are key segment. One is called key, another one is called the counter key segment. It is for mostly for the 5 plus 1 and 4 plus 2 is for the smaller diameter tunnel. 6 plus 1 and 5 plus 2 segments are mostly used for the medium sized tunnel, I can say. Yeah. And 7 plus 1 and 6 plus 2 is for the tunnel dia, which is having more diameter, larger diameter. Then we have different types of segment geometry, trapezoidal, rhomboidal, and rectangular also. Then key segment is most of the time key segment is trapezoidal. That's it. So here I am showing you how this segment ring is installation is going on after when we are it's a the TBM, it's a backside of the TBM that they having separate mechanism to placing all these ring. They are placing all these ring in one sequence. First we are laying the counter key segment, and then subsequently we can lay all those segments. And at the last we are pushing this key segment. Okay, so when we are modeling this TBM tunnel, we've already facing so many challenges. It's first thing, it is not just a simple pipe or simple tube. It's not just a simple tube. You just model along a follow alignment and just model it like internal diameter, which is having some thickness, is just model it. We have to follow some rules and we have to follow some criteria. Those are the criteria. Like first criteria is allowing rotation of subsequent ring, and avoiding position that generate cruciform joints and minimize deviation from. I am explaining you in the next slides. The first criteria, when we are placing the next subsequent rings, the rotation of the subsequent rings is only at the defined position that depends on the number of connection or the connection between them. For example, in this ring, or as you can see in this ring, we have total 16 different connections. So the next subsequent rings can be connected to those 16 different positions only, not to any other position, not to and that subsequent ring can follow any angle. The next major criteria is when we are using this different positions, sometimes some positions can form cruciform joints. Like for example, in this chart, you can see that, okay, if we have position different of 0, it is not creating at all any cruciform joint for particularly 4 plus 2 segments, which is having 2/3 size of 4 plus 2 segments. When the position difference between the current ring and the subsequent ring is 1, then it is also not having any cruciform joint. But see, like when the current ring and the subsequent ring is having position difference of 2, like first ring at say for position number 1, it's the next ring is at position 3, then it will create some cruciform joints. Like for example, here you can see. So it will just make a line. It's a strong line. It's a continuous line. We don't want to break that line. Okay, so we want to avoid this, and then we in this chart we are calculated different positions. Like, okay, which are the invalid positions that will create a cruciform joint, and we want to avoid those positions. But for all these things, we have already taken care of all these calculations. We already taken care inside Python, inside Dynamo script. I will show you later on. And how we are using the minimizing deviation from the TBM alignment. We are placing first ring, and then we are placing second ring with the say, for example, you have a number of allowed position. Yeah, you have number of connections, say n number of connection. Then you have, say, x number of position which can create cruciforms. So the allowed position is n minus x position. So when we are placing this ring, first ring, that can be placed at any location or at any position, but we have to decide that this is our first position and we are placing it. Second position, we just go into iteration, like one by one, choosing from n minus x position, and which position is having the minimum offset from this tunnel central line, as you can see here. Then we finalize, okay, just finalize this position. And then we can subsequently go on going through for the complete alignment line. That's our main criteria for designing for placement of this TBM rings. We already tested few of the tools. We already this Civil 3D toolkit is already available in Dynamo for Civil 3D. We have fewer nodes like you can create. You need some corridor first, and then you can just put some parameter, and you can decide what ring, and then you can just you can make all these rings and make the tunnels. The limitations of all these things is, first thing, these are not parametric. These are generated as a 3D solid element. Okay. And if you want to model those joints and connection details, you have to model it separately. That's why we go for another solution. And the solution is, why don't we? And in COVI, we having this digital development initiative. This initiative, our work is to develop a tool which can do this parametric modeling of TBM rings. First, the parts of this one, the steps in the parametric modeling. First step is first how to get the TBM alignment, because sometimes these TBM are for the train, sometimes these TBM tunnels are for the road. First, and we are getting alignments in the form of track alignments and the road alignment. First, how do we decide that how to get this TBM center line? That's our first point, first step we are doing. The second step is we are how to create a BIM model out of it. Create a BIM model using segmentation of all these sequential rings by minimizing deviation along alignment within project tolerance. That's our yeah. Okay. So next, the first step is the TBM alignment. To get the TBM alignment from the track alignment, we develop some subassembly in subassembly composer for Civil 3D, and then we apply that in the subassembly and run through the corridor, and we are getting TBM central line. And then we develop some parametric families inside in Revit. This example is showing you this. We develop something for 4+2 or 5+1 ring configuration. Here are the sum of the parameter. We provide almost majorly most important parameter already inside this family. Some of the parameters are the family parameters, some of the parameters are the instance parameter, which we can change later on when we are placing those rings. And here is an example of 5+2 or 6+1 configuration. I can simply say total number of 7 segments. Here we have universal ring Revit family for 6+2, for 12+1 ring configuration for the larger diameter of tunnels. Okay, this is the overview of our Dynamo script. Okay, in this Dynamo script allows us to read the TBM centerline point from 3 different data sources. First one is we can directly read from the Civil 3D. If in Civil 3D we have some corridor, we can read corridor feature lines. As I already shown you before, like we generate TBM center line as a corridor feature line. So we can directly read those feature line and getting its points. And we can just input those points to model our tunnel, TBM tunnel. Second data source is we can use 3D polyline or line feature line inside Civil 3D, getting its points and just make it as input and for the placing of this TBM tunnel. And the third type of input we are using here is we can also use CSV, comma separated values, which is giving the coordinates in XYZ format, and we can also use Excel format in this script. And all other inputs are like, for example, we have to just provide what is the ring family we are using, what is our starting position of the first ring, what will be the ring length, your desired ring length, what will be the taper. Okay, just set some value. And this script is also allows us to gives us a liberty. For example, sometimes some rings are rotating, the next position the rings is rotating clockwise, but sometimes in some projects it is rotating counterclockwise or say anti-clockwise. So we already taken care of all these and different types of information in our script. And that second part of the script, we are reading all the family parameter from this ring, And then these are act as an input for our Python script. And in the Python script, we are processing all these data. And by keeping our main criteria that it should not form a cruciform joint and it is having a minimum deviation from TVM central line alignment. And then afterward, we are getting output. Like for example, we are getting output for each individual ring, the starting and end points, starting and end position. And another output is what is the position of that ring, the position which is having a minimum deviation from the alignment line. And then when we run this, so we will have some output check, like we can check, okay, throughout this run, when we are putting all these desired parameter, we have this what is maximum set. In the next slide, I will show you how we are doing, how we did that thing. And then afterwards, we are using those information and creating a ring family and setting up all its instance parameter, for example, taper, start offset, and end offsets. Okay, in this video, we have shown you like, okay, first, we already loaded this ring family, universal ring family of 4+2 ring configuration. We already set up all some parameters in the family. Here you can check all the family which we already set the taper and everything. We load the family inside our project, and then we can cross check about the type property, because these type properties will be treated in the Dynamo script later on. We can change property at what is needed in the project, number of project and the thickness, segment dowels and everything. And then let's run the script. In this script, we are reading information from Civil 3D. Civil 3D file is already open in this system, and with the correct correct corridor, it is having that corridor which is having feature line, TVM central line. We already provide input of a ring family, start position, what is our desired ring length, and what is the required taper or specified taper we need. And we also specify that, okay, we need the counterclockwise. That's why we are setting this clockwise node to false. Then after running, we'll get some result, maybe in 1 or 2 minutes. Yeah. Then we are getting same inputs, running this script. It will take a maybe minute or less sometimes. It depends on the project. Like if you have a very large project, it may take to 5 to 6 minutes also. Then we have all our rings are placed based on our criteria, which we have defined earlier, like minimize deviation from the TVM alignment and do not form any cruciform joints. And each ring is having an instance parameter, or called a parameter, which is showing what is the start offset and end offset of that ring from the TVM alignment. And then the next example I have shown you, the next example is for the 6+1 ring configuration model. The big difference about the previous example and this example, this is a little bit bigger tunnel. It is having only one key. It's having different taper, and in this particular model, in this example, we are using clockwise rotation of rings. We already defined that clockwise rotation in the family also, and we will set it in the Dynamo script. Here are the parameter which we already set here. Like the thickness here is we are using 200 mm or 0.3 meters. One thing I forgot to say that I'm doing everything in meters. So this time I'm reading information, TVM central line information from the CSV file. And now I'm running one by one. You can also run like once in a go. But yes, but if you run it, like you can check the output, like whether the output is correct as per what you want. So here we got all the points from the CSV file, and those points are already transformed to the Revit coordinate system. These are not in the global coordinate systems. When we are reading from the Civil 3D file, we have some nodes that will transform those points to the local Revit coordinate system. Then we got these points, and then we can check that, okay, what is the maximum offset throughout this complete tunnel? If it is within the limits, we run it, we unfreeze that node of creating ring family, run it, And then we have this complete tunnel, which is having all the parameters set. So this is our having ring, which is having all the tapers and positions, and having start and offsets. Okay, in the next example, this is for example for the larger diameter tunnel. Like we are using 6 panels 2 ring configuration model. This time we are reading information from Civil 3D. We already model a corridor of TBM center line with the ring and everything. And TBM center line is represented by a corridor feature line, which is having some point code, which is having a point code of P underscore TU underscore TBM underscore C. We already defined those point codes so that if you want to read particular feature line from there, we can specify in DynamoScript. So this is our ring family, which is having a bigger diameter. The diameter of this ring is about internal diameter is 10 meters and having a thickness of 350 mm. And taper is also much larger than all other rings. Okay, and then we are loading this family into the Revit project and checking all the parameters. And this time I'm not reading this CSV file. I'm reading from, I just freeze those nodes and I just specify what is my Civil 3D file name, what is my corridor name, and what is my point code for the feature line. And I already have this transform node, so it will transform Civil 3D coordinate. I can call the global coordinates Revit coordinate system. Then we have all these results transform, and then we unfreeze this node of a Python script. So this Python script will run, and we run this one, and then freeze this node ring family. We don't want to create a ring family first. We want to check the results, and then we want to create those ring families. We run the script, we check the output, like, okay, it is within the project limits. Okay, then it's okay. And we unfreeze that node of creating ring family instance. Yeah, okay, we can check, okay, how many number of points we're having. And then unfreeze this one, run it again. Then it will create a complete tunnel for you. This example is, in this example, we are modeling more than 2,400 rings. And it will take around 4 to 5 minutes to model all those rings. Every ring is having its parameter, the offsets and everything, so we can later analyze. Okay, in the next slide, or here, I'm saying you like, okay, if you model your tunnel, like, okay, each ring is having start and end offset, though we are trying to that these offsets should be within the project limits. But still, if somebody wants, like if the project manager wants, or if your client want to see it, okay, can I see there's some rings that falls above or like those are out of the tolerance? So for example, here, I'm giving an example. Here in the DynamoScript, I set the tolerance of 0.1 meter, like 100 mm tolerance. And this is a visual result. So we visual check. When we run this script, all those rings which is falls above the 100% of 0.1 meter tolerance, it will be shown as a red color. All rings which is having offset in between 100% to 75%. So for example, here we are using 100 mm tolerance. So those rings are falls in between, like those are having tolerance of 0.075 or 75 mm to 100 mm. Those rings are yellow color now. And those rings are falls below the 75% limit of 75 trigger level, all the rings are will be green. So you can see in the lower left here, this particular ring is a yellow, and then yellow color or amber color you can call. The start offset is 0.0737, which is more than, yeah, which is almost less than the 75%. But the second offset, the end offset is 0.08. It is almost 81% of our 0.1 meter. So that's why it's colored yellow or amber colored. In the next test, we did some clash check also, because we are not sure, like, okay, when we are running our script, we are not even sure, like, okay, whether it will place all these rings correctly or not. Sometimes this ring can be having small topper and then it will clash. So we did our cross check and we did our class check. It's having a tolerance limit of hard tolerance of 0.001, like 1 mm. And we found only one ring is having clash, and that clash is of only 1 mm. So it means that yes, our script is working fine. And here, say for example, in future, like if we want to rotate particular ring, we can rotate ring to any in 16 different position, or maybe the I can call the allowed position, like n minus x, total total positions minus the position which forms a cruciform joint. So we can rotate. Sometimes we need to rotate, and say for example, I want to update the whole of the ring. I can select the first ring, change the whatever the new position I want, run this script, change the position in the input, and then I have to given the path of this file. Here I am using the TBM center line from CSV file. So I have to just select this one, select which ring I want to rotate, select that ring. What will be the new position? I just use the any different position of that depends on number of connections. For example, if this ring is having 16 number of connections, then I can use the position from 1 to 16. And then after this running the script, we have also at the output like, okay, when we are using this particular new position, what will be the maximum offset on all the subsequent rings? Listen and understand this one. When we are rotating one of the ring, it will not just rotate only one ring, it will rotate all the subsequent rings in the follow, and it will try to adjust all the rings and following our criteria, like following our main criteria, not forming any cruciform joints and minimizing deviation from the alignment line or from the TBM center line. The next here I'm showing you, okay, how to extract information from from these rings. Okay, each ring is having its own position. So in this Python script, I have shown you that, okay, you have to select all the things which you want to extract the information and wash, getting as a current DB document and then getting all the element. And in Python, yes, if you are using Revit API or if you are using this unwrap, you have to first unwrap all these elements. And from after unwrapping this element, see, these elements are made up of using adaptive components. So these rings having 2 points, start point and end point. And in this script, I am reading those start end point and end point. So first, I need to get the information about its placement points. We have some methods. We already have a method in Revit API that select that element and get instance placement point element reference ID. It will extract those point as another element, and after iterating through all those elements, we are getting its position and then converting those position to our units, whichever units you want to convert. Like for example, here I'm converting all the units to meters. I'm not using the internal unit. Afterwards, we are getting all these inputs, and then we are reverse transforming. Like we have to transform from the Revit coordinate system to the global coordinate system because we want to generate a table. And then afterwards, I am using another Python script just to rearrange all these nodes. Like we need to make a data ready for Excel. So we need something, and in this Python script, I've also mentioned like, okay, I need some column headings. So I already implemented all these column headings. So this is the output we get afterwards. Like run that script, it will generate a Excel which is having all the ring number selected rings, not only selected ring, and having all the start and coordinates in global coordinate system, not as a Revit coordinates. If you want in the Revit coordinate system, just avoid those nodes. And the conclusion about this, the whole thing, the whole digital development initiative is, yes, we have mostly the benefits of this digital initiative. When you are modeling this as a parametric, it's a parametric ring family. You can change it whenever you want afterwards, without changing, without rerunning completely, without regenerating everything. Yes, this ring location position is based on the criteria like minimum deviation and not forming any cruciform joints. Yes, it is very easy to update the whole tunnel. Okay, if you have a new information, new alignment, a new thing, just run some script because it will update the location of the ring, location position, because location and position is as a parameter, not as a like it's a not a hard coded something. Yeah. Joints and other connection details, like for example, I model this tunnel just with the some segments and not with the complete detail. So later on, if I want to model this, I can just go inside my family and model all those joint details easily. Model all those joint connection detail voids. I can easily model afterwards. I can use those this ring family to place MEP equipments, so it can be hosted on those individual rings. And by modeling these things as an individual ring, I can easily extract parameter, quantities, location of the rings, and everything. And also, this is yeah, because when we are modeling it, we are not modeling it as a complete tunnel, okay, and not as a one complete family. We are using the same family and we are placing that same family at different location. So ultimately, our size will be the minimum, will be lower down. But if we are using separate family for each of the ring, then we have to load all different rings and everything, and then it will just increase your file size. And it is very effectful for the big project. Like for example, here in the previous example, I modeled like more than 2,400 rings, and that that file size is not more than I think 50 MB of the Revit total frame size. And these rings are modeled as though it is modeled as a Revit adaptive component family. We can still divide into the parts. Just click on the ring, divide into part, and we can have a separate segment. We can check that what is the volume of separate segment. We can even assign different materials to those segments. And yes, that's it.